Hello, this is a video on how to take a Lewis dot structure and determine its shape or geometry. And with this shape and geometry comes its, yep, the shape. So by now you should have gotten to this page. And what we need is if you click on here, you need to get to this one, which is the VESPA table, which I already have. And you need the chart, which is the flow rate to determine molecular geometry, so you need that. You need the VESPA table, which is this. You need the example of the handout, and then you also need the blank copy of the worksheet. And the blank copy of the worksheet is actually a downloadable if you click on here, this worksheet for molecular geometry, and it's actually a PDF. Okay, like that. Okay, now I'll bring it up a little bit more, a little bigger, so that you can see it. It's actually right there, so I don't need to do it anymore. Just to let you know, there's 4 blocks. You fill in one of them per substance or problem. So each of the pages you can do four problems. Okay, so at this point you should have been able to figure out its Lewis dot structure, which is a pictorial representation of showing what atom is sharing electrons with what other atom, how many electrons they're sharing, usually said as single, double, or triple bonds, and how many are not being shared, which are usually stated as lone pairs. So what we now need to do is we now need to take that two-dimensional thing and make it into 3 dimensions and give it a shape. To do that, we use what is called the VSEPR theory. I screwed up the spelling. I call it VSPER, but it's actually VSEPR. Okay, and it stands for valence shell electron pair repulsion. And what that means is that if you think of atoms as negative spheres, because the electrons are on outside, so you actually other things see a negative sphere, you say that every atom is a negative sphere, and every bond, and it doesn't make a difference to the type of bond, single, double, triple bond, is a string, then what happens is doesn't make a difference how many, those negative spheres will try to get as far away as possible. That's what the repulsion part says. The first 4 letters basically means that it's the valence electrons, and they're always in pairs, that basically we're looking at. But we knew that from Lewis dot structures. But it's the repulsion that makes it, that helps us figure out the shape. So if you look at the first flow chart, okay, molecular geometry usually comes from knowing the bonds and how many atoms there are. And this is my little flow chart, and I'm using logic for this. Okay, you do this for every single substance. You start at the number 1. You see if the substance fits the number 1. If it does, it's that shape. Then you go to number 2. And if it doesn't fit number 2, then you go to number 3. There's no jumping around. Okay? It's a logic tree. So the first one says that any two atoms, it's just the substance just has two atoms. That has to be linear, no matter the type of bond. Also, if you have three atoms and there are no lone pairs on the central atom, three atoms or more, you have to have a central atom. And there are no lone pairs on the central atom. Again, it doesn't make a difference. The type of bonds, single, double, triple, doesn't make a difference. That's also going to produce a linear shape substance. All linear shape substance have what they call bond angles. And an angle, just like in geometry, requires three things. In this case, you need three atoms. Outside atom, central atom, outside atom. So technically, if you only have two atoms, you don't have a bond angle. But we make pretend because the bond angle goes with the geometry. So even though two atom substance doesn't technically have a bond angle, we say it's the bond angle of linear, which is 180. If you have three atoms and the central atom does have lone pairs, then what happens is those lone pairs are a big negative thing. And that big negative thing affects the outside atoms, which are also negative things. And what they do, that lone pair does, since it's a bigger negative thing, it pushes the outside atoms closer together, so therefore it's no longer linear. What is it? Well, we'll get to that later. So that first section is basically looking at just the number of atoms. If your substance doesn't meet those criteria, and it's not one of those two things, then you go down to 2. Now, number 2 is my simplified way for level 1 kids. If you're listening to this in an AP, you have a lot more. You have a lot of other things to do. So there'll be another video to help you along, and you're using this just as an introductory. Okay, but for level 1 kids, if you have a double bond or a triple bond, and it doesn't make a difference how many there are, if you have a double or triple bond, what I'm going to do is I'm going to make your life easier, and I'm going to say, we're not going to get specific. We're just going to say those substances will be planar. And the planar molecule or substance has an unknown bond angle because it actually can have different bond angles. And you usually don't call them planar, you usually have more specific names. But again, right now I want to simplify it for you. So we'll call it planar. Planar basically means a substance or shape that has a planar symmetry to it. In essence, if you slice it, it'll look the same above and below. Okay? And that will make life simpler for you. Something like carbon dioxide, which has two double bonds and no lone pairs in the central atom, well, it would be planar, right? No, actually it wouldn't, because it fits the criteria of number 1. Three atoms, central atom has no lone pairs, so it would be linear. So you wouldn't even get to number 2, because you would have finished off at number 1. So if the substance isn't 2 atoms, 3 atoms with a central atom, no lone pairs, and it doesn't have double and triple bonds, it's the third one, which is a substance that has all single bonds. And when you get to all single bonds, you got to use the table. So the table isn't for everything, it's just for singly bonded substances. So let's get the table. So for this table, Okay, the most important column is the first column, and it has a weird wording. What it means is, and now again, the next thing we're going to do is simplify things, even though even though that the outside atoms make a difference, we're just going to look at the central atom. Okay, and what the first column is saying is, how does the central atom deal with the rule of 8? If the central atom follows the rule of 8, that says 8 valence electrons around it, shared or not shared, which means it has 4 pairs of electrons, then it's going to be one of the rows that says 4 on it. The 5 and 6 are the ones that exceed the rule of 8, and 2 or 3, well, number 2 is 4 electrons, and the only element that wants only 4 electrons is beryllium, and the only one that wants 6 electrons, 3 pairs, is boron. So 2 and 3 are for beryllium and boron. Most all of the 3 rows that are 4, and then some can exceed. Okay? So then what you do is, so 2, 3, 5, 6 are just one row, so you just name it. And the names are the way they are, and you got to memorize all these things, so somebody's going to create some kind of way of explaining how to memorize it. That won't be part of this particular video. So what's left are the 3 in the middle, the 3 with the 4s. So what happens is, if you have 4 single bonds, 4 outside atoms, they're singly bonded, no lone pair on the central atom, you would think it would be a square, but we're in 3 dimensions, so what it ends up being is a thing called tetrahedral. And the tetrahedral has bond angles of 109.5, and they're all exactly equivalent. So if you think of it as a triangle, a pyramid, that's basically if you took and touched or connected all of the outside atoms to each other, it would look like a pyramid. Okay, that's what the tetrahedral is. Now, if you only have 3 single bonds in one lone pair, what happens is that lone pair is very negative, so it will push all the outside atoms away from it, and the outside atoms get closer, and then what happens is the central atom becomes the tip of the pyramid, so it's called pyramidal, and the atoms are closer together, so the bond angles are closer, 107.0. So that's if you have 3 single bonds, 1 lone pair. If you have 2 single bonds and 2 lone pairs, this is the classical case of water, then what you have is what is called bent. And what the weird thing is that due to the starting tetrahedral shape, your lone pairs are on the same side of the central atom. And the outside atoms are on the same side. That's counterintuitive. You would think that the lone pairs would try to get as far away as possible, but they don't. So they're on the same side, which causes it to have a bent shape and causes the bond angle to get even smaller, since now you have 2 sets of negativeness, so the outside atoms are going to be even closer together, so the bond angle goes 104.5. So that's how you determine the shapes of and bond angles of singly bonded substances. So with the table, now we'll look at the table. Here's an example of the table. So again, each of the blocks is an example. Here's CO2. So we do the Lewis dot structure. Figure out the total number of valence electrons, the correct showing of work, and then we describe it. The number and types of bonds, well, 2 double bonds. Is there a central atom? Yes, there is. And if you want, you can put C for the central atom carbon here if you like. And the number of lone pairs is LP, stands for lone pairs, on the central atom carbon is 0. So if you go through our hierarchy, which is, so you look, 3 atoms, central atom, no lone pairs, it's linear. So it's a linear molecule, bond angle 180. Hybridization we'll deal with in another video. Okay. And now is another example, NF3, excuse me. Total number of valence electrons, 26 electrons, again showing work. We try single bonds, and what we get is we have 1 lone pair. That works. So the number of types of bonds is 3 single bonds. Is there a central atom? Yes. Circle Y. If you want, you can put the N there. Okay. And 1 lone pair. If there are no central atoms, you just write Na on the line, and you know it's linear. Okay, no matter what the type of bond it is. So now we have 3 single bonds, 1 lone pair. So we go to our shape, our flow chart. Is it 2 atoms? No. Is it 3 atoms? No. Is there a double or triple bond? No. Now we're going to go, it's all single bonds, which is our table. We go to our table, and what we do is we look at the central atom, nitrogen. It follows the rule of 8, so it's looking for 4 pairs around it. So you go to 4, and in this case we have 1 lone pair, 3 single bonds, or 3 single bonds and 1 lone pair. That name is pyramidal, and it has a bond angle of 107.0. Pyramidal, 107, bond angle, and I said this is an example. So you don't have to write this. I said this is since they're all single bonds, they're coming from the VSEPR table. Okay, and this hybridization actually is sp3, and this is sp2, whatever that means. And again, you will find that out in a different video. So that's how you do it for all of them. Again, each block is 1 problem. So if you have 8 problems, you're going to have 2 sheets. And if you don't have the sheets, you can go on the back and do the same exact thing. Okay? So, recapping, what we're doing is we're using a flow chart and a table to come up with a logical way of, once we know what the Lewis dot structure is, we can then use VSEPR, valence shell electron pair repulsion theory, meaning that all the atoms are negative bodies and all the bonds are strings, and they will try to get as far away as possible from each other in 3 dimensions, and that is the shape. And that will give you a geometry. And if you look at it, that's why I made those 2 sentences up on Lewis dot structure, because they help you in using this flow chart, the table, and the VSEPR theory, because it's only the lone pairs in the central atom that really influences the geometry. The outside atoms are still negative spheres, no matter how many lone pairs. That's why the central atom lone pairs are so critical. Okay? Yeah, hope that was understandable.